So last lecture, we started discussing the conservation laws that govern any physics, including mass conservation and conservation of linear momentum. We saw the mass conservation in material form as well as spatial form. So if you go back to the previous lecture, we started by discussing all engineering applications do obey the laws of physics, which starts with mass conservation and momentum conservation, which in your prior courses you would have learned mass conservation is like saying mass cannot be created or destroyed. So we are still within the descriptions of classical physics. So we assume that mass cannot be produced or destroyed. So we have to, that is the principle, but how do you derive a mathematical form to apply for a continuum particle, which will be J rho equal to rho naught. And this equation is applicable at all points x bar in a particle which is denoted as uppercase X, material X. So if you have a little blob, I kept giving an example of taking a blob and hammering it into a sheet. All points in that material or that sample that you are subjecting to hammering will obey this relationship where the density at any given point is related to the density of that point or that particle in the reference configuration multiplied by the J, which is the, if you recall what is J, is the determinant of the deformation tensor. That is, if deformation tensor is known to you, or in other words, if the deformation is known to you, you can calculate J, you can calculate changes in density at any point in that material. But the question becomes, how is F known, or how to get x equal to phi of x from basic principles, or how do we describe the deformation that comes from solutions to the conservation principles or conservation laws in spatial form. So if you look at it as a particle, you would write this equation. A particle description or a material description inherently requires some knowledge of the deformation, which has to come from a solution to the spatial equation. So the story is unraveling as in all of chapter 2, we kept saying here is a deformation F. Now compute all these matrices or measures based on F or velocity gradient. How do you get F? You have to solve the basic equations of how the density and velocity are related to each other. This equation in index notation is written as partial rho over partial t plus the derivative with respect to the spatial variable of rho times pi. This is called the conservative form. I didn't say that last time. And rho times del dot v equal to 0. This is called the non-conservative form. This is a fundamental difference that I told you last time. This is an algebraic equation, whereas this is a initial boundary value problem. Which is governed by a partial differential equation. So to obtain solution for density as a function of position or time, you need to know both. I mean, you need to solve this equation, but this also has velocity. So you can't solve this equation by itself. You need some information about velocity. And that comes from momentum equation, which we are going to see today. So this is the summary of last lecture. Okay. Any remarks or questions before we go on? So all this is covered in section 4.1 of the text. section 4.2, balance of linear momentum. Okay, what do you know about balance of linear momentum? What do you know about your Newton's second law?
Body in motion tends to stay in motion.
That is Newton's first law. That talks about inertia. Newton's second law says the rate at which the momentum of a particle changes is exactly equal to the external force that is acting on the particle. This is Newton's second law, written for an individual point-like particle. Newton's second law for a point mass. Point mass being it has no shape, it has no size, it's just a point with a mass m. You've seen this in high school, I'm sure, right? So we want to first understand this is for a single particle whose velocity is, let's say, v, and is being subject to a force F. This by itself is not very useful for us. It is perhaps useful in the example where you have your baseball hurling across the park, and you can describe the trajectory of the baseball depending on the force that it experiences due to drag or due to the batter hitting it, and that can be described using this equation. Now, if you take the other example where you take a little blob of material and you're hammering it into a sheet metal, this equation by itself is not useful there, although you know the principle is still the same. So first we need a form of Newton's second law for continuum or continuous medium. For a continuum system or a continuous medium. So if you have a material that is, we assume it's a continuous medium, it is made up of, I mean, you can choose a small segment or piece of that material. Let's say it is a tiny blob that looks like a cube. And we say this has a volume of dV. And if you multiply that by the density, you get the mass of that element. Basically taking a piece of metal, taking a small portion, which we call an infinitesimal volume. And if the local density is rho, if you multiply density times dV, you get the mass of that little element. Okay. We want to ask the question, how to write this equation here, how to write d over dt of mv equal to f for an infinitesimal block of material. That is our first goal for the unit. Is the question making sense to you? This is not a rigid body. It has a shape. It will have a deformation. It will change shape, etc. How will we write this equation for a tiny blob of material? That's our first goal. Okay. So I'm going to erase this for now. All right. Here's your blob. Okay. We write change in momentum of the blob. If I write that is dl, dl is equal to change in, sorry, dl is equal to x dot, the velocity, times dm. If you want, I can write this. That is the momentum of a small element. It's just mass times velocity. So if I ask you what's the momentum of a bullet, it's the mass of the bullet multiplied by the velocity. I'm here taking a small blob whose mass is dm and who is having a local velocity of v or x dot. So the momentum is dl. So I should say not change in momentum. The momentum of the blob or an infinitesimal amount of material. So if this small little blob contains x dot times dm, then the total momentum is dl over the volume of the particle or the body. So that would be integral x dot dm, which is integral x dot rho dv. And you know as well as I do that when I write integral over the body, this really stands for a triple integral over the volume. So this is the total momentum of this entire medium whose size could be finite, which is described by the integration limits. So if I want to calculate dl over dt and equate that to force, this is basically Newton's second law. And I would write, since to denote, this is the force on the body B and it's an external force, so we'll write it F external. What is L? L is d over dt, integral over the body, x dot rho dv, and this is equal to F external on B. You're with me so far? Yes. Let's leave the left side the same and let's focus a little bit on the right side. Okay, you take a little blob of material and you're hammering it. What are the kind of external forces one can think of that can act on such an object? The impact, right? Okay, what other forces?
It's gravity.
Gravity and any other force you can think of?
We count intermolecular forces.
Sure, intermolecular forces. You can think of electromagnetic or electrostatic forces. You can, if you put that little blob of material under the ocean, and as it sinks further and further, what other force acts uh, on that blob? That is a type of intermolecular force.
The external pressure.
The hydrostatic pressure, which is squeezing that material from all sides as it goes deeper into the ocean. So among the lists that came up, gravity, electrostatic force, intermolecular force, surface like hydrostatic pressure, compression, or even tension, or any kind of surface stress, you can see there is a major difference between the two forces. On one hand, you have forces like gravity that act on you anywhere you are. So when I'm holding this cup of coffee, the liquid inside it, the cup, everything is being acted upon by gravity, and it is not even in contact with Earth, which is the major source of gravity. But if I were to apply a force, something like hydrostatic force, I have to literally come in contact with the surface of the object. If your object is here, and if you want to apply a force on it, you literally have to touch it and squeeze it. You can't squeeze it from a distance. So external forces can be majorly divided into two groups, which are called body forces that act at any distance of separation from each other, and surface forces. Okay, body forces and surface force. The simplest body force we can think of is gravity. Why? What is gravity? Gravity is m times g, which you can write density times volume times g. Okay, so if you want to write the total force of gravity, you can write this is equal to integral over the shape of the body rho times g dv, where g is acceleration due to gravity. Or you can even think of g as force per volume. You can think of it, it's like a force density, force per volume. Because the other term is volume, sorry, the other term is mass, it's force per mass. That is what we call acceleration, right? So we can write F external that is acting on the body can be split as F body plus F surface. Body forces and surface forces. And the body force, we write FB. We can write this is equal to integral rho B dV, where B is the force per unit mass. I'm just generalizing gravity because it's a very simple example. I can write rho g dV. And instead of calling it G, I'm calling it B, where B is like a generalized force per unit mass. Okay. You may ask me, do all forces scale with mass? Suppose you take like this cell phone and you electrically charge it, and you bring another charged object near that cell phone. Of course, they are going to interact, either attract or repel each other. But that repulsion doesn't have anything to do with the mass of the cell phone or the mass of the other object.
So yes, maybe.
Well, the answer is actually no, because electrostatic force, as you know, is proportional only to the charges, not to the mass. If suppose you put two objects, Q1, Q2, you know the force is Q1, Q2 divided by the distance squared. You're with me so far? When they start moving, how much they accelerate each other, their mass has a role, because what is acceleration? Force divided by mass. So the force itself doesn't care about the mass, the electrostatic force, but the acceleration does care. So we are in general interested in anything that scales with mass, which we call the B, okay? Because we are doing continuum mechanics where gravity is most often the important external force. So for us, it will work most of the time. Okay, so we are going to write body force is rho times B dV. And what about surface force? How can we think about surface force? How will you quantify surface force? Let me give you some hints. Yeah, you want to say something? No. So if you are dropping a spherical object under the ocean, if it travels to a certain height below the level, what is the hydrostatic pressure if your object has traveled to a height h below the ocean surface?
Coming to a what?
So let's say this is your ocean or sea level. If you keep an object here, it's being acted upon by atmospheric pressure, let's say. If you drop it in the ocean and if it reaches a height h or a depth h and it's here, what is the pressure acting on this object from your basic hydrostatics knowledge? If this is atmospheric pressure, the pressure at this level is atmospheric plus the weight of the weight of the liquid that is above that level. So Pa plus density of water times G times H. Okay. So this is hydrostatic pressure, which is very easy to think of because it's basically a spherical object being compressed by the same pressure from all sides. That's why I brought up this example. It's easy to think about. Imagine, close your eyes, you can imagine a sphere and a vector that is, or a force that is squeezing that sphere radially from every direction. You're done imagining? Okay. So if I ask you, what is the force on a sphere at this depth? What will you say? At every point in that on the surface of the sphere, it is being acted upon by this amount of compressive stress. What is hydrostatic pressure? It's compressive stress. So how will you compute the force? So if you know the stress, or if you know the stress tensor, you will multiply that with the area and then integrate over the surface of the object. I wrote it in mathematical form, but the basic idea is at every point in that sphere, there is a vector that is pointed inwards. All you have to do is multiply that vector and integrate over the area of that sphere. And how do we do surface integration? We take the dot product of the quantity at that surface, which is represented by, so let's say you have a sphere. If the little patch is dA and it's pointed outwards and n cap, okay, we try to take, if we want to calculate what is the force or what is the stress at this point, we try to calculate or we try to get the stress dot that with the unit vector, which gives us force. This is an example. This is not a principle. I'm not giving you a proof or anything. Just to help you visualize this, I'm asking you to think about hydrostatic pressure, which is the simplest of loading. So this is the for hydrostatic pressure. What is the form of the stress tensor? How will you express it? You know it is like minus P because it's compressive and it's the same value. There is no dependence. That is, this P is the same value at every point, regardless of where the point is. So there is no theta dependence or phi dependence or R dependence. There is no dependence on anything. So it's just a scalar and it is acting along the radius only. So you will write this is minus P ER ER. And what is N cap? N cap is basically ER. Because area, if you take any patch on the sphere, its area vector has to point outwards radially, which would be ER. So this quantity here, sigma dot n, is basically minus P ER ER dot ER. So this is minus P ER. So if I want to get this, this is minus P ER dA integrated over the area of the sphere. We are not going to do any integration because this is P is a constant. It's the same value everywhere. What is integral dA? This is minus P. And you have to integrate over the surface, which is going to get you minus P times area. So the total force with which this hydrostatic pressure is squeezing your object is just the pressure multiplied by the surface area. Okay, so this is not a proof. I'm trying to illustrate to you one possible scenario where the stress has a very simple form. Okay, I'll maybe give you a minute to finish writing and then I want to make a somewhat important point. Everybody is having emergencies this evening. I mean, your classmates, some of them coincidentally have a lot of things going on this evening. I should maybe bring back the attendance quiz and then the emergencies will go away. All right, are we good? Can I erase this and continue? All right, this is, let's see how far we can get through this. So stress at a point or the stress tensor and traction or force on a material surface T. And the important breakthrough relation we are going to learn is T is equal to sigma dot n. All right, let's talk a little. What is the origin of stress? That is, you take a continuum material at any given point, you will have a certain stress. which we know is a tensor. But what makes it a tensor, and what is the origin, or where does this stress come from? So the intermolecular forces are sometimes attractive in nature if they go a little bit farther. If they get too close, it is actually repulsive, right? I don't know if you know this already, but you take two molecules and just two molecules. If you work out the mathematics, the potential between them is repulsive if they are very close, and if you are above or after a certain distance, it becomes attractive. So negative is attractive and positive is repulsive. So molecules, you can just simply think, if they are squeezed too close to each other, they repel each other. If they are pulled apart, they try to resist by attracting each other. So everyday experience confirms it, right? You can't take any material and just do this and split the material. It takes considerable amount of loading in order to break something or separate the atoms. And that is because of this long range attraction between the molecules. In addition to this, at any given in a given material, you may apply external loading, which could be compressive, tensile, or shear loading. Okay, so if you apply a certain loading externally, all that eventually becomes forces between molecules, and we quantify those forces through a stress tensor, which could have many different components. As you know, we can write stress tensor as a matrix sigma 1 1, sigma 1 2, and so on. This is the collective response of atoms. At the core of it, I want you to understand stress is defined at a point as a collective response of many number of atoms to external and internal forces. Are we together so far? But we have a problem in the sense that, atoms are real. We know that. But what we think as a continuous medium is not real. That's the theme of this course. We talk as though there is a certain continuous medium which is infinitely divisible, but you and I very well know that is not the case. There is a certain limit to what can be considered as a continuous medium. So when we go from stress at a point to a force, you can't talk about force without talking about what is the area over which this force is acting. How I would say this is, let's say you take a bunch of atoms. Okay, if you are down to the atomic level, you can't really talk about their individual positions because atoms are never at rest, they keep moving up. But if you zoom out and if you look at a large number of atoms, they together organize into some kind of a structure or an area. And once you see that there is a geometric shape to that area, you can define the value or the magnitude of that area and its orientation. And then you can say, if the stress at a point is given by sigma, what is the area on a material surface? Or sorry, what is the vector force on the material surface? So you can take a membrane, it is under a state of stress. What is the force on that membrane? It is the stress integrated over the area, which is what we are writing here. If you think that in a given material, a point is at a state of stress sigma, and you have an area that is encompassing that material, the local force is essentially the projection of the stress onto the orientation of the area. How do you understand that? Suppose you have a object which you are shearing. You put your hand or you try to machine it using like a file, and you are applying a shear force. At that instant, what is the normal or axial force on that object? If your force that you are applying or the stress that you are applying is tangential, what is the axial force? I have my block I am shearing it. I'm not doing anything in the axial direction, neither compressing nor stretching it. What is the force in that direction? Zero, because the stress that I am applying is tangential. The area vector is perpendicular. So if I do sigma dot n, in the perpendicular direction, there is no force involved. If I do sigma parallel to n, then there is something involved. The making sense? That is, the math may come later, but I want you to intuitively understand, if you have a shear force, the shear stress, the force is acting along that direction. In reality, force creates stress. So how do you do a tensile testing? You hang a weight, let's say 10 pounds, 30 pounds or something. You take the weight, load divided by area. That's what your stress is. Load divided by area. In the mathematical terms, we define stress as though it is defined at a point and then integrated over an area to get a force. So it works backwards in continuum mechanics, where we think stress is a fundamental quantity and force is a derived quantity based on the stress and the local orientation. Whereas in reality, we think force is a basic quantity and we derive stress based on it. But here's the catch. When you take 30 pounds as a weight you hang on an object and load it, do you think every point in that cross section is exactly experiencing the same stress? Why not?
Which the weight it's sitting on, or say it's like a bridge, one in the middle, would experience the most likely.
All right, I'll give you an example. I'm agreeing. Suppose you have a test sample with a surface which is perfectly planar surface, and we hang a load of, let's say, 30 pounds. If every point in that surface has the same orientation, you can think that they are all experiencing similar loading conditions. Now, suppose you have a sample that has a notch in between, and then you are hanging a load of the same 30 pounds. Do you think every point in this cross section, or along this line experiences the same kind of loading? Tell me intuitively what's happening.
The points down to the left and right, those are probably experiencing less.
They are experiencing tension. The points on this line and the points on this line, they are experiencing axial tension. The points on this line and the points on this line, their orientation is whatever this is, 90 degrees perpendicular to them. If this is pure tension, how can this also be pure tension? You tell me what it can be. It has to be shear, pure shear, right? If this is pure tension, this has to be pure shear.
Can you explain about how that's tension?
So think about this surface, perfectly planar. All I'm doing is I'm applying load. I'm trying to displace all the atoms in the vertical direction.
I see that. So the left is tension.
This one?
Yeah.
Yeah, this is all pure tension. Every point is subject to pure tension.
Okay, and then the right.
On the right, all the points on the horizontal line are subject to pure tension. All the points on the vertical line are subject to pure shear, because if this is tension, 90 degrees to that should be pure shear. And everything in the middle is also subject to pure tension.
I'm confused because the weight seems to be attached to the part that's above. So I would have thought the tension would be above.
Okay, if you want, I can redraw this.
Oh, okay, sorry.
What I meant to illustrate was, suppose you have a notch that looks like this. Let's say we glue we have let's say we have gorilla tape. Have you used those to like high strength adhesives? Let's say you attach it to every surface, and then you try to put a hook, and then you put it on your car or your bicycle and you try to rip it apart. You are basically applying loading. So if this entire surface is coated with adhesive and you are subjecting it to a force, at this surface it is being pulled axially, whereas in this surface it is not being pulled axially, it is being pulled along the surface, or in other words being sheared. You can take another example where your cross section looks like this. Let's say it's like a wedge. You apply uniform loading along this cross section. You know as well as I do that this cross section is subject to both tension as well as shear because the loading is oblique with respect to this direction. So the generalization from this is that the force at any given point is obtained as the stress tensor at that point multiplied with the local orientation. If this orientation is like this, it's easy to understand. It's just purely axial. If the orientation were like this, the local vector is like this, and you will have to obtain tension or traction equal to sigma dot n. And if you want to get it for the entire surface, you would multiply this by dA and integrate over the area. This discussion started by us writing external force can be split into body and surface force. Body force is rho times B value, which is force per unit mass. And then surface force can be written as integral over the surface sigma dot n dA. This sigma dot n, if you refer to the book, is given a symbol called T, where T is the traction vector. The main takeaway is that stress is a point property or is thought of as a point property because its origin lies in intermolecular forces, whereas force, you can't define force without telling on which area is that force acting. You can't say force at a point, force has to act on an area, not at a point, because area has an orientation. That orientation is what decides whether the force is along a particular direction or what is its magnitude and so on. A point doesn't have orientation. Only an area can have orientation. Remember that. Point is basically like a sphere which is shrunk down to a value in which its radius is not defined or orientation is not defined. So a point cannot have a orientation. Only an area can have orientation. So this relation T equal to sigma dot n is equation 4.18. It's called the Cauchy stress tensor or the Cauchy stress principle. And you can also write this as, actually this is called Cauchy's relation. Cauchy's relation. And of course, since you are writing a vector on both sides, you can write Ti equal to sigma ij times nj. So we wanted to get the material and spatial form of momentum conservation. We wrote Newton. Okay, I'll write it here because there are a lot of things that I'm going to say. So we want to get material form of momentum conservation for which we wrote the integral of momentum integral that is L is equal to integral over the object rho dm times x dot. That's where we started. And then we want to write rate of change of momentum, which is dl dt, which is d over dt of integral rho dm x dot, and this is equal to external force acting on the object. This is where we started, just to retrace our path and continue, because we took an exit and we went to a town. Now we have to get back on the highway. So this external force, we are now writing F body plus F surface. So I'll continue here. Right here, F body plus F surface, and F body is equal to rho times B dV, where B is the force per unit mass. F surface is sigma dot N dA, where sigma is the stress at a point, sigma is stress at a point in the material, and N cap dA is the local area vector. So I can write integral or d dt integral rho dv x dot is equal to integral over the volume rho b dv plus integral over the surface sigma dot n dA. So this left side, we apply the Reynolds transport theorem. We are going to get integral over the volume d dt of rho dv x dot is equal to integral over the volume rho b dv plus integral over the surface sigma dot n dA. I'm going to rewrite this as rho x double dot dv over the volume. Why? Because density of the particle or density is not, yeah, it's not time dependent, and then we are just taking the derivative of the velocity here. So this equation, that is combining this, is the integral form of momentum conservation for a finite sized or a finite object, or in other words, the material form. You have something that is finite. This relationship holds true inside the volume and across the surface of that object. Now, in our matrix, this is the material form, and we would still want to derive the local form, right? That is the spatial form. So we'll start here. Integral rho x double dot dv over the volume is equal to integral over the volume rho v dv plus this term here, integral divergence of v dv. We used what is called as the divergence theorem, which we saw very briefly in unit 1, which is to say the integral of a the integral, let's say b dot n dA over the surface is equal to divergence of b, or divergence of b dv across the volume. So the reason we do this is to convert everything into volume domain so that we can write rho, this is x double dot, which we'll write as rho v or rho v dot minus rho b minus, wait. Got a mistake here. Oh, it should be divergence of sigma. Minus divergence of sigma, the whole thing dv over the volume is 0. I'm just rewriting this so that I bring all those the other two terms to the left side. I write them under one integrand multiplied by dv, and if this has to be 0, then the only possibility is this is 0 at every point on the body. So we write rho b dot equal to rho b plus divergence of sigma. This v dot we can write rho times the local acceleration is rho times b plus divergence of sigma. Momentum conservation or momentum balance in spatial. So you can also write this in index notation. This is rho ai equal to rho bi plus sigma ij times nj. So in our matrix, this is the fourth relation, which is the general form of momentum conservation in a field or spatial form. We just see a couple of variants or like different ways this equation is written. I think I'll have some time to do some examples maybe. So rho A equals rho B plus divergence of stress tensor. In fluid mechanics, rho A is often written as the partial derivative of rho V plus the divergence of rho VV. What is the quantity VV? Is it a scalar or a tensor? Yeah.
Um, the, um, would be, I think a tensor.
It is a tensor. Second order tensor. You can think of it two ways. One is if you write V is VI EI, then VV is VI VJ EI EJ. So it's a second order tensor. If you consider V itself as a direction, VV is a diad. Remember exam 2 problem, you had a quantity that is A, not exam 2. Exam 1, where A is a vector, arbitrary vector, and you form a diad as AA. Okay, so this is similar to that. So what is the index notation of this? This is rho AI equal to the partial derivative of rho VI plus the divergence of rho VI Vj. What should I do here? Is it xi or xj? Should I put xi or xj?
Because like for yeah.
Rho. Rho. So should I put xi or xj?
Say I.
You're saying I. Anyone else saying anything else? I.
We should put J because on the left side it is I, so it should iterate up.
You should have j to be a repeating index. That's what this divergence is. Or if you're not sure, you can write partial over partial xk ek dot rho vi vj ei ej. You will be left with partial over partial xk rho vi vj and then ek dot ei. You will get delta ki times ej. So wherever I and k appear, you can make them the same. So this has to be I. Well, I of course you said I here. Well, j is just a dummy index. All it matters is I should be the one that is different repeating, and j is the non-repeating one. If you want to call the non-repeating one as I, you just have to call the other one j. Okay. So in this notation, partial derivative of rho vi plus the derivative with respect to xj of rho vi vj is equal to rho bi plus divergence of sigma. This has to be partial over partial xj of sigma ij. So this is commonly used in fluid mechanics. In solid mechanics, especially if you don't have any motion or if you are in an equilibrium situation, if you are in conditions of mechanical equilibrium, mechanical equilibrium, you can write A equal to 0. So this would be 0 equal to rho b plus divergence of sigma. Here's an exam question if you are given this statement, how would you explain this statement in words? What does it mean? Rho B plus divergence of sigma equal to 0 at any given point. What is the interpretation? So this first of all, this relation is applicable at any point in that object or in that medium. At every point, it is satisfied. That's what equilibrium means. So it's like saying the external force at any given point is balanced by the internal stresses or internal forces. And this sigma, the sigma is related to x and x dot. Or in other words, it's related to strain and strain rate. Of course, without knowing what that relation is, you can't use this equation. But at a very basic level, it is a force balance that talks about how the external and internal forces are balancing each other. Based on the relationship between stress and strain or strain rate, what do we know about materials? Give me some examples of materials. I'll start the proceedings. Linear elastic materials. What are they defined by? We have stress linearly proportional to the strain. And if you can write sigma is equal to Young's modulus times strain, this is example of a linear elastic material. It's like your metals before you go past the yield strength. Okay, this is one example of a relationship between sigma and the strain or stress and strain. Can you give me another example of a material behavior? Something, a relationship between stress and either strain or strain rate. Sure. So you want to write sigma is proportional to epsilon power n, where n is so something that looks something like this. How will you describe this slope in practice? What material? So describe what happens here as your strain increases, as you put more load or as you deform this material more, it becomes easier to deform. Okay. Easier or harder?
The shape of the graph, I think it might be archaic if you be downward.
So I always get this backward. So if you have this where it okay, this becomes harder, this becomes easier. That is, to get more deformation, you don't have to do more work. Here, to get more deformation, you have to do a lot of it. This is called strain hardening. As you apply more strain, the material hardens. Can you give me an example of a material that behaves like that from everyday life? it gets harder to deform it as you keep working with it. Metallic alloys. Okay, now give me example for a material that becomes easier to work with as you deform it more. What kind of a material is toothpaste? Does it get easier to work with a toothpaste as you do it, as you deform it more or shear it more, or it gets hard? Initially, it is like a solid until you put it in your mouth and start. What is brushing? Brushing is shearing, right? Until you start shearing it, it looks like a solid. But the moment you start shearing it after a threshold, it behaves like a liquid. You can keep deforming it. And you can continuously deform a lot without doing too much more work because the material literally becomes like a fluid. So for your metallic alloys, you can say strain hardening. For, I don't know if strain softening is a word, but the more common word is, it's called Bingham plastic fluid. It's initially plastic and then it becomes like a liquid. It's a type of behavior. So the point I'm trying to drive is, depending on what is the relationship between stress and strain or strain rate, you could have different material behavior. So a material is not just about physics, it's also about what is its own inherent constitutive behavior. What is the most common material we encounter? Like fluid, common fluid that we encounter. Water, right? Depending on who you ask, most people will say water, some people can also say air. But air or water, they both have a common behavior in the sense that they are called Newtonian fluids. And why are they called Newtonian fluids? If you have air or water, and if you apply a shear stress, in response to the stress, what is shear stress? You displace the atoms that are at the top. Those atoms will try to pull the next layer along with them, and that layer will pull the next layer along with it, and this will propagate all the way back until there is a wall. So a velocity gradient develops. Velocity gradient, that sounds very familiar, right? What is velocity gradient? Partial v over partial x. In this case, it's just partial v2 divided by partial x3. Because this, if you call this direction, partial x1. You call this direction 2 and you call this direction 1. This is basically v2 over x1. And we can call this strain rate. If the stress is linearly proportional to strain rate, that is called a Newtonian fluid. Another example. The principle is, in general, sigma is a function of epsilon and epsilon dot. Or actually, I should write, it's a function of position, velocity, or velocity gradient. So I just want to add two sentences. Every material has a constitutive model or behavior and if you know that constitutive law, that is, if this equation is known to you, then you can use it to evaluate what are the internal stresses which are balanced by external stresses. But we are not going to discuss this in much more detail. This is actually given in chapter 6 from the book, which you can kind of take a look. Okay, but it's not something we'll be testing in the exam. Okay? But it's good to be aware. All right. We have time to squeeze in one example. Problem 4.3 from the textbook. If you have your book with you, kindly take a look. We are going to try that problem. Okay, problem 4.3. I hope you have seen it. Problem reads, in an ideal non-viscous fluid, there can be no shear stress. Hence, the Cauchy stress tensor is entirely hydrostatic. Sigma ij is equal to minus P times delta ij. That is in index notation. Can you write that in tensor notation? If I write sigma ij is equal to minus P, a scalar, multiplied by delta ij, that is same as writing sigma is equal to what? Times identity tensor, right? So we are asked to show that this leads to the following form known as the Euler's equation of motion for a frictionless liquid. That is, we have to show minus 1 over rho gradient of P plus B is equal to the derivative of velocity with respect to time plus gradient of V dot P. So you want to start with this equation here. Rho times A is equal to rho times B plus divergence of sigma. This is the momentum balance equation. This is true always for any material. We are told our material is a frictionless liquid whose pressure is purely hydrostatic or whose stress is purely hydrostatic. So what is divergence of sigma? That is divergence of minus P I cap. Okay. What is this divergence of I cap? So this is partial over partial xj minus P EI. EJ has already been dotted away. So this is basically like writing minus gradient of P, which is a vector, or minus partial derivative of P with respect to xj. Should write EJ. EJ. Yeah, I'll keep it as I. That's the one we usually use. So we will have minus gradient of P xj ei delta ij. Okay. So I'll have ek dot ei, which is delta ik delta ij, and then I will have ej. So I in the end I'll have only j, which I'll write minus gradient of p xj ej. And since we don't like j, we call it I. So that is one of the terms on the right side. What about the second term? That is this term. Rho times b, you can just write this as rho times bi ei cap. So if you write the right side, that is equal to rho times bi minus I have gradient of p, or derivative of p with respect to xi. Which I can write, this is equal to density times pi minus 1 over rho partial derivative of p with respect to x. So I already have the right this part here. Over here, what is rho times a? This is rho times, you can write this as partial derivative of b with respect to t plus gradient of b dot v. This is basically material derivative. So if you combine the two, in index notation, this would be rho times partial vi over t plus what is gradient of v? That is partial vi over xj times vj. So you can easily show, or you can easily derive, if this is left side and this is right side, there you go. There's your relation that you need to show. So what is the type of problems that you can expect in this topic? Some kind of a constitutive law will be given. I will provide that in the question, and I will ask you to derive the form of the momentum balance for that type of material. That making sense? I'll tell you it's a plastic material, or it's a Newtonian fluid, or a viscoelastic fluid, or I'll tell you this relation, and I will ask you to compute or show some kind of a momentum balance for that material. This is the type of problem you can expect on the exam. I think it's also the same that is on the homework as well. Have you started the homework yet? Not yet? Okay, maybe now at least chapter 4 homework you could do. There are only like 2 problems. Okay. Okay, this is a good